In this second video for section 8.2, we're going to discuss inverses of functions. And we have several videos on this. Inverses of functions is a very, very important concept. What I would suggest would be that you go through the practice and do a bunch of problems just composing functions, just what was in the very first video of this series. For chapter 8, and just do a bunch of those until you've really got it down before starting this section, because otherwise you're just going to be completely confused on this. Okay, and if you do understand the previous stuff, this part of it hopefully will not be too confusing for you. Okay, so the definition, let R be so we're going to start with relations. Remember that a function is a special kind of relation. And so this definition works for relations and then is made more specific for functions. Or rather, it's applied to functions. So the definition, let R be a relation with elements represented by ordered pairs of the form A, B. And of course, for this class, remember, those are ordered pairs of real numbers. We're back to real numbers instead of any old function or any old complex numbers. Okay, we're using real numbers here. So it's just a set of points in the real plane, is all that says. The inverse relation, which is written R to the minus 1, and we read that as R inverse, R to the minus 1. That's not the R for real numbers. That's just the R for relation. It's the name of the relation. I named it R instead of, like a function we would name F. Right? So the inverse relation R inverse, R to the minus 1, of R is the relation given by this. So remember, relation is a set of points. So this is equals by definition. That's that colon equals. So R inverse equals by definition the set of all points B comma A such that A comma B is an element of the relation R. So if A plus B is in R, then if A comma B is in R, then B comma A is in R inverse. And the inverse turns out to be true as well, the converse. If B comma A is in R inverse, then it turns out that A comma B will be in the relation R. Okay, so they're inverses of each other, R and R inverse. Seems a little weird at first, but that's the way it works. So all we do to find the inverse of R is we just switch the first and second coordinates of each point in R, and that will give me the set of all points in R inverse. Some people say, oh, you switch the x and the y. If the variable of the first coefficient is x and the variable of the second coefficient is y, then you're switching the x and y coordinates. Okay? So for example, this is a simple example with just 4 points in it. It's a relation. It's just a set of points. All those points are different from each other. And what I'm going to do is write the inverse relation. So that's the first relation. Notice we don't have R of X or anything. R is just the name of the relation. It's a set of points. R inverse, you can see what I did here. I took 1 comma 5 and I switched it with 5 comma 1. I took 3 comma 8 and switched it with 8 comma 3. 3 comma 9 becomes 9 comma 3. 5 5 just stays 5 5 because, looks the same if you switch the two 5s. Okay. Now notice when I do this that the domain of R inverse is the range of R, and the range of R inverse is the domain of R. In other words, the range and domain are switched when you go from R to R inverse or from R inverse to R. right? So remember the domain's a set of all first coordinates. So with R, it's going to be 1, 3, 5. And the range of our inverse, that's the domain of R. The range of our inverse is 1, 3, 5, right? The range of R is 5, 8, 9. And the range of our inverse is, the domain of our inverse is the same as the range of R. It's 5, 8, 9, right? So they just switched. The R and R inverse switched domain and range. The inputs of one become the outputs of the other. And the outputs of the first one become the inputs of the other. So they're switching inputs and outputs. Well, okay, so that's the end of that one.